So Megan Downing posed this question on Twitter. Would the orbit of something around a torus-shaped object be stable? Torus-shaped object is basically a donut, at least in 3 dimensions it's a donut. Could it be stable? Could it pass through the center and maintain orbital motion? Generally, what would this look like? Any thoughts? So I said I would try it out in VPython. Of course, we're going to consider motion close to the torus-shaped object because farther away from the torus-shaped object, you can treat it like a point mass, just like you do with anything else, and you'll get your normal orbit. But we want to see what we can do with the torus-shaped geography of the thing we're orbiting around. So what I've done here is set up a code that will create several different particles, each of which is going to be a source of gravitational force. So I'm keeping that in a list called atoms, giving each of them a different position, giving each of them a small amount of mass. And then so these are the things that will be orbited around. So this is, here we will create the thing to be orbited around. And then here we're creating the satellite, the thing to do the orbiting. So create the thing to orbit, to do the orbiting. There we go. And so this will be a satellite. We're giving it a position out here. We have to give it a velocity, and we'll turn on its make trail. We're not going to worry about velocity for these things because we're going to keep the thing in the center stationary. We're not going to make this more complicated than it needs to be. And we come down here to our usual Euler-Kromer loop. We start out with the satellite's force being 0, and then for each of the atoms, we calculate the relative position vector from the atom to the satellite. And so that atom will exert a force that's given by negative g, the 2 masses multiplied together, the unit vector of this relative position vector here, and then divide by the magnitude of that relative position vector squared. So this probably looks familiar, g m1 m2 over r squared, and then the unit vector just tells us what direction to point in, and the negative sign means we point toward the source. So these things will always be attractive. Then we update the satellite's velocity. We add to the previous velocity the total force divided by the satellite's mass times the time step. Then we update the satellite's position. We add to the previous position the satellite's velocity times dt. And we keep looping over and hopefully get an interesting trajectory. So I've tested this with a basic cube shape. So we've got 8 atoms here arranged in a cube. So when we run this, press Control 2 to run. All right, so here's our satellite going around the cubic object. So remember, it's experiencing a gravitational force that is the sum of every gravitational force from each one of these atoms here in the cube. And you can see you still get a roughly elliptical shape. I think it's getting a little bit distorted when it gets close to the edge or to the corner there. But yeah, it should still obey the same general rule. It's just not necessarily going to be a perfect ellipse. So what we need to do is replace this cube with a torus. So we'll start by commenting these out. I'll keep these commented out just in case we need them again. So let's see. So to create a torus, I first need to create a circle and then kind of copy that circle around in another circle. So let's see. So let's suppose we make the circle's radius 1. Do I want a radius 1? Let's go with radius 0.5. I'll change it later as I need to. And so I need to rotate around theta. So I'll start with theta equal to 0. I need a d theta equal to 2 times pi divided by, let's say, actually, yeah, let's say n here, the number of particles that we have here. And we'll say while theta less than 2 times pi. And then we'll do, let's see, I need to go atoms.append a sphere with a position given by, actually, let's calculate the position off to the side here. So let's calculate position equal to, so for a circle, that's going to be r times vector cosine theta sine theta 0. But I want this circle to be moved over a little bit. So we'll say minus, let's say r times vector 1, 0, 0. I'm just using r as a scale there. So this is going to take my circle, it's going to move it over to the left 1 radius unit. Okay, so we'll say position equals position there. What else do I need? I need mass equals dm, radius equals 0.05. That closes up the sphere, that closes up the atom, so that should be all we need. Oh wait, as always, I need to increment my theta. Theta plus equals d theta. And we'll do Control 2 to run. All right, there's the circle that I wanted. Obviously, I'll want to do more data points to get a smoother circle. But you can see this thing's moving around, and actually this should work out pretty well to give me... I was about to say it'll work out pretty well to give me an ellipse, but we're seeing the roughness of it here because the thing is not closing back in on itself. We're getting a much different orbit than we got. Because basically when it gets closer to here, it's detecting the force from these much more strongly than it detects the force from these. So we're already getting a different orbit here, which is pretty cool. All right, so that's pretty neat. Let's just see what happens when we add in more data points. Let's get this up to 16, which is double the number of data points. Now, in principle, this is going to slow down the code because with each step it's having to do 16 vectors instead of just 8. And in principle, the more I make this circular, the more I should be able to just replace this with a point right there. So let's now try to get our torus. So here's what I'm going to do. I'm going to turn off the animation for right now. So we're going to make this just a 0 because I want to just get the geometry correct. I want to make sure we end up with a proper torus here. And so what I need to do now is take this circle and kind of rotate it about this way, make more copies of it. So let's see, I need another angle. Let's stick with the R out there. So I need another angle. Let's call it phi. All right, then I'll need a d phi. So I need to pick the number of circles I want to create. So n is currently the number of points in the circle. What if I use the same n here? And then my dm is going to be mass divided by n squared because I'll have n times n atoms. And so now we'll need to say while phi less than 2 times pi. So now I'm setting up my phi loop to wrap around my theta loop. So I'll need to take the entire theta loop here and indent it. And then I'll come down here, backspace, and increment my phi. Phi plus equals d phi. Oops, need to get rid of that d there. So phi plus equals d phi, good. So I'm resetting theta over here. So the piece that needs to change is where I am. Well, actually, there's 2 pieces that need to change, right? I need to change the position here. So let's see. So I need to change the center of my circle here. So this is going to move. So let's think about this. This is going to move around in the XZ plane. Let's actually go ahead and exit that. So I'll need to modify this to be cosine of phi and this to be sine of phi. So I'll have a new central point. All right, so here I'm going to need to also rotate my circle. So the way I can do that, let's think of it this way. When I start out at phi equals 0, I want to be over here. So that means that, let's see, I'm modifying these two, right? Yeah. Because the sine of theta, this part, the y component, is going to be the same regardless. That's right. So like, for example, this thing is going to need to get a cosine of phi. And then this will need to get I believe this will need to get a sine of phi cosine of theta. Because basically I need to be able to exchange the z part with the x part. I think that'll work. Let's see. Okay, cool. We've got ourselves a torus. It's a very narrow torus. Oh, yeah. So this hole is going to have 0 width. So this is the part where I need to increase this r here. Okay, so let's call these a couple different things. Let's call this RC, or radius of circular cross section. Okay, good. And then this needs to be radius of torus itself. Okay, so if you take a circular slice out of the torus, this will be the radius. If you then measure the basically the center of the torus going around, this will be that radius. So I need to replace this with an RC and this with an RT. All right. See if that gets me what I want. Okay, cool. Yeah, that's a torus. That's a nice donut shape there. Okay. Now, I'm going to have to move this thing out significantly. Actually, maybe I won't. I don't know. Let's see what happens. Let's turn the DT on. The worst that happens is I have to go back and fix it, right? Here we go, Control 2. Okay, there goes the satellite. Oh my goodness, there it goes. Okay, it's going through the object, which is not really allowed because this thing is supposed to be like a torus-shaped planetoid or something like that. But yeah, no, that's pretty cool. So, okay, so in answer to the question, it is able to go through the center. I ought to be able to just modify the initial conditions. Let's do a couple things, though, for visual sake. Let's, for the satellite, let's make its radius much smaller. So let's go maybe like a 0.01. Make sure it looks through, and let's give it a different color. Let's make it color equals color.red. Okay, and now what I would like to do, let's try having it go maybe faster in the Y direction. Let's try 1.0 here. That might get it to fly away. All right, so there it goes. All right, yeah, I think that's on a hyperbolic orbit. So let's try making it go fast. Actually, no. Let's have it go slower and put a little bit farther away. So let's make this a 3. Because now I have the size of the torus to contend with. All right, cool. It's descending here. I think we're about to get we might be getting our stable orbit around the torus. Oh wow, this thing looks so cool. And of course, if you want this to be more filled in, more torus-like, you just increase the number of data points, but I think this is good enough for demonstration purposes. This is looking like a stable orbit. It's not overlapping back around itself, which is to be expected. I mean, we couldn't get that very easily with a circle approximated. So this is pretty neat. I think this is going to stay bound. Let's put this in fast motion to see. Okay, so this is looking pretty stable. I think it's just going to keep precessing around there. That looks like it's going to do us pretty good there. So here's what I'll do is I'm going to leave a record of combinations that work. So let's call this one a precessing orbit around torus. We need basically I have to copy and paste the position and the velocity. There we go. Now what I'd like to do, we want to see if we can get an orbit that goes through the center, right? The easiest way to do that is going to be to start out in the center, leave it, and then see what happens. Rather than trying to shoot from here into the center, I can just start in the center, have it come out, and then see what it does. So here's the deal. I don't know how many tries this is going to take me. So I'm going to keep trying different combinations of position and velocity. And what you will see next is either fast motion, me working through that, or a compilation of my great failures. Coming back? Is it coming back? It's coming back. It's coming back, y'all. Oh, it's coming back too fast. It's coming back too fast! Oh my gosh, I think we got it. I think we got it. Yes! No. Crash. Oh man. All right, that first part, we had it. We had it right there. We had it right there. Ooh. Ah, there you go. There you go. Come on around. Come on around. There you go. Okay, it's precessing a little bit. That could cost us in a little bit. All right, this one's made it through several iterations here. I think we might have it. I think we might have an answer to the question. Yes, you can get it. I don't know how long this will last, but yeah, it looks like you can get it. So yes, so in answer to Megan's students' questions, yes, you can get a stable orbit around it. That's pretty straightforward to do. And it looks like you can get a stable orbit through it. That is pretty cool stuff. So thank you to Megan's students for suggesting the question, and thank you all for watching. I will see you next time. Bye-bye.